So looking at page 35, number 6, we're looking for the arc length parameterization for a circular radius A, traced out by the vector value function r of t equals a cosine t, a sine t, if you're thinking about it in component form. So first thing I would do is rethink or reconceptualize this as a variable function. So let t equal u of t, which we can designate as just a u for simplicity, I suppose. And so I would make this r of u is equal to a cosine u, a sine of u. So r prime of u, negative a sine u, a cosine u, the magnitude of which, square them up, simplify. I've done this one enough where it's pretty clear what it's going to be, but just in case, factor out the a squared. You're going to have sine squared u plus cosine squared u, which goes to 1 because it's a Pythagorean identity. Square root of a squared is equal to a. And so what we're going to do is integrate in order to find the arc length. We're going to integrate over the interval of t sub o to t, deciding that t sub o could be whatever we want. We're going to decide upon 0 to t of the magnitude, which we discovered just now is a, integrate that with respect to u. It's actually kind of it's a nice byproduct that by letting t equal u of t, or t become u of t, or really just kind of looking at it as, and I mentioned this in the previous class, that u of t is equal to t, it was sort of like defining u of t itself as a linear function. The fact that we're redefining it as a different variable allows us to write an expression through the integration process in terms of t based off of that magnitude. And so it's kind of like we're allowing the vector value function to kind of be this amorphous moving blob, I guess, out in space. Really a cross section of the blob, traced out by a plane intersecting that blob. It gives you the periphery, and that's some floating. If you kind of visualize the nexus, if you've ever seen Star Trek Generations, just kind of floating out in space, and by pinning it down where u of t is equal to t, we're locking it into position, right? And so we're working with it in its most general form, but then when we get to a point where we're saying, okay, now we're only focusing on the interval going from 0 to the linear function t, r of t equals t, or I'm sorry, u of t equals t, then we're limiting it so that it's pinned at the origin and only extending as far as what we decided t is. It's very abstract, but it's also very cool. So a u over the interval of 0 to t gives you at. All right, so s is equal to at. All right, which means that t is equal to s over a. All right, now that t is in terms of, because really a is constant multiple, we could write this as 1 over a times s, but we could also think of this as the same as being t of s. So in our original vector valued function, which for simplicity was written as r of t, but it could have been r of t of anything, we are now pinning it down by saying, okay, well, we're going to replace that t as a function t in terms of s. So r of t is equal to a cosine t, I'm just rewriting it, comma, a sine of t but now we're thinking of this guy as T of S. So R of T of S, the composite function simplifies down to just R of S, can be thought of as A cosine. Now, the T of S is replacing the T. Nothing really new there. All right, but now since I know that T of S and 1 over A times S are the same thing, I can say A cosine 1 over A times S, A sine 1 over A times S. And now we've parameterized our vector value function in terms of arc length. So again, as you know, this is the vector value function that represents a circle. And that circle with varying radius A can now, instead of being represented by its relationship to some fixed point out in space based off of, that's one hell of a circle, right? You know, so just thinking in terms of like the unit circle, for example, we always pin it at the origin and say, okay, it's locked onto a point at the origin. We have this vector, and how it relates as it moves around the circle is defining our vector valued function. It just so happens that these arrows trace out a circle as it works its way around. All right, that's R of T. What we're doing now, by converting it over, and the quality of this circle, I mean, it looks so much like an ellipse. It's just so terrible. But what we're now doing is comparing each point to the points that immediately precede it, or the points that precede it along its path. And so all these points, for example. So I'm going from one point to the next, and we're looking at the little relationships. I can bring it in a lot. The little relationships that exist as you transport, I guess, from one point to the next. You know, you do a little over up, little over up, little over up, rather than saying we're going from this location, which is pinned to the x-axis, to this location, which is also pinned to the x-axis, if you decompose into the component vectors. We're looking at it with respect to the points that immediately precede it. So that's some of the value behind an arc-like parameterization.